Hi, we saw already that this set theory leads to among other things, the Boolean algebra with operands and, or, and not. The set theory is also the fundament and leads also to another topic, which is relations, and we talk about it today. Now, there are three ways to represent relations. You can draw them, you can define them by pairs, and there's another way to do it, which I will show you in a minute. To draw relations, it's really very easy. I have two sets, set A, set B, with the elements 1, 2, 3 and the elements 5 and 6. And for instance, I can say, okay, 1 has a relationship with 5, 2 has a relationship with 5, and 3 has a relationship with 6. Now, each relationship, obviously, I can also represent by naming it a pair. So, relationship with 1 to 5 is the pair 1, 5. The relationship between 2 and 5 obviously forms a pair 2, 5, and then 3, 6 is then the other pair. And in fact, I have here a new set of 3 pairs. Now, this is the moment I want to introduce a product. Now, products we have had before. This, however, is not the regular products we know already. So it's not like 2 times 3 equals 6. It is not the dot product between two vectors leading to some kind of scalar, or it is even not the cross product between two vectors leading to a third vector, C. It is none of that kind. It is called the Cartesian product, A times B. And it means that I have a set of pairs where each element from A has a relationship with each element from B. So I need to add this. So I have here another pair combining 1 and 6, 2 and 6, and the relation 3 and 5 needs to be added as well. And now my set of pairs, ordered pairs, has 6 elements. Now from these, obviously you recognize here the coordinates, so the third representation is a very straightforward one. I have here the numbers, the elements of set A. I have here the elements 1, 2, 3, 5 of B, and the set of pairs is then represented by these 6 dots. Hence the name Cartesian. Okay. Now, what do we know about this Cartesian product? Let's have a look at this. First of all, if I want to multiply this Cartesian product with a scalar, like for instance 2 or 3 or in general n, this is the same as multiplying A by n, multiplying B by n, and take the Cartesian product between the two. In our case, if n would be, for instance, 3, the pair 1, 5 would turn to 3, 15. Both are tripled. Well, this is really obvious. Then the second question is, does the law of does the commutative law apply? So is it true that A times B equals B times A? Well, we can be very brief on this. In the first product, for instance, one of the ordered pairs would be 1, 5, 1 being an element from A, 5 element of B. In this case, however, the pair would be the other way around, and obviously this does not lead to the same set of pairs. Third, thus the distributive law applies. For instance, if I would have A times B intersected with C, would that be the same as the product between A and B, the product between A and C, and the intersect of those two products? And the question is this true? Now, if you want to prove it, you want to have prove it both ways, from left to right and from right to left. We start with the first one and say, okay, if I have A multiplied by B intersect with C, then obviously I am talking about pairs x, y, where x is an element of A, y an element of the intersection of B and C, which means that x is an element of A and the y is an element of B and C. Now, since I multiply here between the two, it means that x needs to be multiplied with y being from B. So one pair would be an element of the product between A and B, and the other element would be an element of the product A times C. Well, change this for the intersection sign and there we are. You see that the A times B intersects with A times C. And in a similar fashion you can prove it the other way around, starting with this part and then going back to the next one. If you look on page 120, you will have to prove there as an example. Okay, since we are introducing this subject, we talked about what the definition was of a Cartesian product. We looked at some of the properties, and now we are going to go and dive a little bit in the different kind of relationships there are. Now, this is not really math that answers a question. It is simply setting up the system and have you a little bit, give you a little bit of a feeling of what we are really talking about. Before I start, I go back to this Cartesian representation. Now, we saw already that if we have the y-axis and the x-axis, and we have here several points, so we have here the elements 1, 2 and 1, 3 and 4, and we have here the elements 2 and 3, then obviously the result is a set of dots. And this is in fact my relation and the result of A times B. Now, if now A is not defined as the three elements 1, 3 and 4, but if A equals now the set of X and being an element where X every x is okay as long as this x is an element of R, all the real numbers, and x is between 1 and 4. So instead of having only these three elements, I have the interval going from 1 to 4, 1 and 4 included. If I do the same with B, I have here all the elements x, where x is an element of R, and for instance every element is okay as long as it is between the 2 and the 3. What would be then the consequence for this drawing? Well, since every element is part between, from these intervals, is part of A and B, I think every point in this rectangle is then part of this product, and this would be then my answer.